Hi and welcome back. So in the last video, I started going over the three different types of discontinuities, and we only got through one in the last video. We got through the infinite kind of discontinuity. So in this video, what I want to do is I want to start talking about the second type of discontinuity. So I'm going to write down this is the second type, and that is what we call the removable. Removable. Or I learned this as the removable discontinuity. This is sometimes, I've also heard this referred to as a point discontinuity. And it's called that because you're really only having a discontinuity at one point. You're not, and even I guess you could argue that there really was a discontinuity only at this one point of 0, but the difference in the last example but the difference in that we're going to see in this example I do in this video is in this example the function went to infinity. There wasn't a finite point anywhere that we were approaching. Both sides of the graph went to infinity there. So in this example, what we're going to see, and actually let me do an example. And let's use for this graph, we're going to use the example. Actually, I've been using f of x a lot. Let's say h of x is going to be equal to, let's say, x minus 2 divided by x minus 2. And maybe you remember this. This is from, maybe this looks kind of familiar to the very first video on limits that I did in this playlist, where I think the example I had in that video was just x over x. And we said that, it's really tempting to just be able to just want to cancel this out, to just go like that and say that that's equal to 1. And really, when you're graphing this, you can think about doing this. But the problem is that this function, and I'm going to actually undo all of that, the problem with canceling that out and just saying that this is equal to 1 is that if we plug 2, if we took h of 2 and we threw the 2 into this function, we're going to get 0 over 0, and this is undefined. This is undefined, which, importantly, is not equal to 1. So at the point 2, we can't say that this function is going to be equal to 1. But pretty much, and hopefully you don't mind if I kind of rush through this a little bit, graphing, because hopefully you can see, for any other x value I plug in, if x is pi, if x is 5, if x is 17, even if x is 0, our function is just going to be, let me get back my orange color, our function is just going to be a line at y is equal to 1. And the only place that we're going to have it be undefined is right at that point, x is equal to 2, right there. And so this is pretty much the reason that this is called a removable or a point discontinuity is because this is our point. There's one point, or I don't know if there even has to be more than one point. Typically, in these examples, there is not going to be more than one point. There is going to be one. Actually, we will see some examples where there might be 2 points of discontinuity. But typically, when you see this, there is only going to be one point. There's only going to be one removable point of discontinuity. And that is why it's called the removable or point discontinuity. So if we were going to say, and let's just see if this fits, see how this fits with our definition of continuity up here, where we have to check the limit from the left, the limit from the right, and also the value of the function itself. And hopefully you can see hopefully you can already see where this particular function is going to fail that test. But anyway, let's just go back down, scroll down, and let's just do that test. So the first thing we want to do is we want to take the limit from the left-hand side. So the limit as x gets really close to 2 of our value of our function h of x. So we want to take it from the negative side. So as we choose numbers that are really, really close to 2, as we move closer and closer to 2 for our values of x, well, it's pretty obvious what we're going to approach. And this is, we learned this in the first video, I think, that it's pretty obvious that we are just going to approach 1. And similarly, let's try if we were going to approach from the right-hand side, if we were going to approach from values that are just a little bit larger than 2, that's going to also be equal to 1. I'm even just going to write it just like that. We're going to say equal to the limit as x approaches 2 from the positive side of our function h of x. So hopefully you can see in the video where we define continuity, we have satisfied these first two conditions, which means that we can even say if we were going to just take the overall limit of this function, if we were going to take the overall limit as x approached 2 without any preconditions, without any condition of saying it's coming from the negative side or the positive side, just if we take the overall limit, we know that this exists, that this is defined, and that this is equal to 1. That as we choose values closer and closer to 2 from either side of our function h of x, we're going to get closer and closer to 1. So anyway, hopefully you can see that we've met these first two conditions, and now we're going to see, hopefully, where we're going to fail the test for continuity. Because remember, the last part of our test for continuity is that our function has to be defined at this point 2, at our point that we've been concerned with, at the point 2. Our function has to be defined as this same number that we've been getting for all of these different limits. But we know, we already figured out in the very first part of this video, that h of 2 is undefined. So, therefore, we fail the test for continuity. This is not a continuous function. And the type of discontinuity we have is we have a removable discontinuity, sometimes also called a point discontinuity. I'm probably just going to be calling it a removable discontinuity because I guess that's what I learned it as, a removable discontinuity. One other thing I just want to mention about removable discontinuities is that we could say, I've got another graph down here, and I might even go and get myself another graph for the next. Actually, you know what? I'll just write it down here and maybe erase it real quick. But if we were going to say, let's actually define another function. If we said g of x is equal to x minus 2 over x minus 2, and we said that it was going to be defined for this for all x not equal to 2, and then we're going to say that it's equal to, I don't know, say it's equal to 3. G of x is going to be equal to 3 when x is equal to 2. So if we were going to do that, and we already figured out in the last part of the video that this is just going to be a line. This is just going to be a line at y is equal to 1. And we're going to have this removable discontinuity right here. But now I've defined this as a piecewise function. So I'm saying that for all x where x is not equal to 2, we're going to define it as this function. And when we have x equal to 2, we're going to define our function as just being equal to 3. So that's 1, 2, 3. And now you might be asking, well, I can, for every possible x value I choose for this function g of x, I have my function defined. So even if I chose 2, I still have the function defined as 3. And you might ask, well, does this make it continuous? And hopefully you can see that it wouldn't, because again, our same condition, this condition 3, where in the last video we said h of 2 is undefined. In this example, we would say that g of 3, it's not going to be undefined, it's going to be equal to 3, but the problem is that the limit of all the other points is equal to 1. That the limit of all these other points is equal to 1, and this is not equal to 3, and 3 is not equal to 1. Therefore, we still have a discontinuous function. We still have a removable discontinuity here. However, and one thing I'll just do really quick, if we were going to still have our piecewise defined function, and instead of a 3 here, we were going to say that this is equal to 1 for x is equal to 2. And I should have, actually, I just realized I should have said that that should have been a g of 2 there, instead of a g of 3. Sorry, I made that mistake. But if we were going to define this g of x minus 2 over x minus 2 for all x not equal to 2, but then at x is equal to 2, we define this function at 1. So let me erase that point right there. And we said g of 2 would therefore be 1. We would just fill in that point right there. And then, even though this function it's a piecewise defined function, then this would be a continuous function. Continuous function. Even though we've still got this guy sort of, I guess, rattling around in there, this guy is still going to be undefined at x is equal to 2, but we've defined the function. We've actually done a separate definition of our function. We've said at x is equal to 2, our function is going to be equal to 1, and 1 is equal to the limit of what the function is actually approaching there. So that's why this would be a continuous, this would make it a continuous function. So anyway, hopefully that was understandable. Hopefully you got that, if we still had the removable discontinuity there, if we still had the hole there, and we defined it somewhere else, that wasn't where the hole was, I guess, that wasn't where the limit of what the function was approaching, if it wasn't where that limit was at, we would still have a removable discontinuity. Typically, and one of the things I do just want to say, and actually I'm going to end this video pretty soon too, one of the things I do want to say is typically you're not going to have the function defined somewhere else. Really, the only time you're going to define the function somewhere else, like somewhere completely unrelated, is when you define a function like this, where you have a piecewise definition of a function, where you say for some values of x, the function is going to be one thing, for other values of x, it's going to be another. That's really the only time that you get stuff like this, where you define the function. Let me actually see if I can just erase. Oh, that was actually pretty good. If we had something like this, where we have an open circle there, a removable discontinuity there, and we define it somewhere else, you're only really going to see this when we do this piecewise definition of functions. Typically, when we have removable discontinuities, and when we start doing limit examples, you're going to see that almost all of the limit examples are going to be removable discontinuities, or at least I should say most of the really interesting ones that we're going to be looking at are all going to be removable discontinuities. But typically, this is what they look like. They're just a removable discontinuity. The function is undefined at one point, and it's not going to be defined anywhere else. We're not going to have one dot up there. We're just going to have a one point where the function is just completely undefined there. So anyway, hopefully that made sense to you, and I know I'm getting through these kind of slow, but I do just want to make sure that I explain everything having to do with these discontinuities. So now we've gotten through two of the different types of discontinuities, the infinite and the removable. And really, pretty much all of the, I guess, limit examples we're going to do in this playlist are all going to be either infinite discontinuities or removable discontinuities. But there is one more type of discontinuity that I want to get through. So I'm going to end this video here and then make the video on that discontinuity right now. And then, I promise, we'll finally get to some real examples of problems that you'll see. So anyway, thanks so much for watching, and I'll see you in a future video.